Okay, today we're going to look at the probably what is considered the hardest part of freshman chemistry, the stoichiometry or weight problems or whatever however you refer to them. But they are sometimes considered very difficult. So I'm going to show you a better way. And it's based on the concept that an equation it gives a count of the number of particles of every type that's involved in the chemical reaction. And that number we count as moles, and it means 6.02 times 10 to the 23rd particles of whatever we're looking at, atoms, molecules, ions, whatever. A mole of anything is 6.02 times 10 to the 23rd of them. Now, when you look at the balanced equation, it's showing the number of moles of each of the reactants that are involved and the number of moles of products of each one of them that's involved in the reaction. But we can convert moles of sodium sulfate or whatever to grams. So the balanced equation is also giving you a mass of all of the things that's involved in that balanced equation. So I know the mass of everything in the reactants when it's balanced, and I know the mass of each one of the things in the products when it's balanced. And of course, the balancing process is designed to make the law of conservation of mass uh, obey. So we wind up with the same number of grams of reactants that we do as products in this when we balance an equation. Now, if I look at a balanced equation and it tells me the amount of all of the substances, but moreover, if I focus on any one of them, knowing how much of that one is there tells me how much of everything else is there. So once you have the equation balanced, the amount of every substance is known if you know the amount of any one of them, because the equation is balanced. Now, I told you stoichiometry problems are often listed as the most difficult aspects of freshman chemistry. Uh, and it's partly because of the way it's presented. It's usually presented in a rigid series of ordered steps. That is, typically there's 3 steps. You have to do step 1 before you can do step 2, and you have to do step 2 before you can do step 3. And you have to get step 1 right before you can get step 2 right. You have to get step 1 and 2 right before you can get step 3 right and get the problem right. So um, we go through such a, I don't know, it's obsession, I think, is a good word for the way chemistry professors and chemistry high school teachers view moles. They want to make everything go through moles, and it doesn't have to. It is correct, but the steps they always tell you to do is take the mass that's given and convert it to moles. Then take the number of moles of that substance and go to the balanced equation and get the number of moles of the other substance. So we convert moles to moles. First step, we're converting mass to moles. And second step, moles to moles. And the third step is to take the moles that we got in step 2 and convert it to mass. Now, let me show you why that's so. A problem is considered difficult if I miss it, right? If I get it right, I think it's easy. But if I miss it, then I think it's hard because I have to go back and learn what I did wrong. Okay, so this is the reason why people think freshman chemistry is difficult and hard. It's because, let's suppose, for example, step 1, you have a 50-50 chance of getting it right. It's probably better than that, but let's just bear with me a minute. If I have a 50% chance of getting the first one right, and 50% chance of getting number 2 right, and 50% chance of getting number 3 right, what's the probability I'll get the whole problem right? Well, it's 1/2 times 1/2 times 1/2. That's 1/8. So that means you got 1 chance in 8 of getting the whole problem right if you could miss any one of those 3 steps by a 50-50 chance. So that means that statistically, a very large number of people are going to miss that problem because they went through those steps. I recall vividly when I taught at Western Kentucky, I taught a course that we kind of among ourselves called poets chemistry. It was for non-science majors and typically arts and humanities majors would take that particular course. And it was very much watered down, if you want to use that phrase, compared to our regular Gen Chem course like you're in. And I could not bring myself to teach anything called chemistry that didn't address the stoichiometry. And math problems gave these students hives. I mean, they would just get scared to death of anything that resembled math. And so I'm trying to figure out ways of teaching this, and it's really, really getting to me because I, like everybody else, I wasn't having a lot of success with doing it. But I recall real vividly one morning we're going to have an exam over this, like you will Wednesday. And my office was in one building, and the lecture hall was in another building. And they were joined together by a covered canopy and walkway. And you went in on, I could go in from my building directly onto level 3 where the lecture hall was. And there were doors leading from the canopy walkway into the building. And I happened to walk into the building a few steps behind 3 or 4 of my students that was going to the class. And I was really feeling good about it. I thought, man, you know, if I ever got this right, I did it this time. I'm ready to do the fist poke up. Yeah, I got it. Well, I walk through the door and I hear those students walking in front of me, walking down the hall, going mass to moles, moles to moles, moles to grams, grams to moles, moles to moles, moles to grams. And I knew I didn't need to grade the papers. I knew they didn't get it because what they had done is just what you did in high school. You memorized an algorithm for doing it. And all you got to do is just make a tweak somewhere and you're going to miss that problem. And sure enough, I got disappointed. I was expecting great things and great things didn't happen. But I'm really obsessed over this. And one night when in my sleep, I'm even dreaming about this. And I visualized in my mind, in my dream, I saw myself move one of these numbers. I had set them all up to do this, all these 3 steps all in one. But I, in my mind, saw moving one of the numbers in the denominator of the first factor over to the denominator of the second factor. And wow, that hit me. And I'll show you what that leads to in just a moment. Okay, but this is the method. And the reason why it's hard, it's memorization without understanding. There are some things you have to memorize. You have to memorize vocabulary and words and nomenclature and sometimes speed of light or you know, Avogadro's number is probably a better. So there's certain things you do have to memorize, but you need to minimize that. You need to memorize just the tools you need to work with and then learn how to use each of the tools. That's the whole idea about learning something. Memorization is short term. You can really practice up and probably do really well on exam 3 coming up. But if you do it by memorization, you won't remember it on the final. And that's not what we want to do. We want this as much as possible to come natural to you. And it does by practice. And it does if you learn the best way and the quickest way that you can be successful. And so that's where we're going. Okay. Now, the other thing, and I've seen it already in this class in grading some labs, it's presented sometimes as a mathematical exercise devoid of any chemical understanding. It's ratios and proportions. This is to that as that is to that. Okay. Well, that will work. But the only problem is when you do that, all your units cancel out. Things, you can put the numbers, one of the factors in upside down, and it won't even be obvious that you did that. And that's going to cause you to miss the problem. So ratio and proportions do work. The multiple steps do work. But there's a better way. Now, it's based on the concept that you balance an equation. When we had you do that for the quizzes and exams over balancing equations, we insisted on balancing the equation with the smallest whole number set of coefficients. That's so that, typically in regular semesters, I'll have over 100 students in one of my classes. And I don't want 100 right answers to have to dig through on exams and quizzes. And other professors feel like I do. And we all require people to, if you've got an equation that's got all coefficients or even numbers, well, you can divide a 2 out of that and have it balanced again. So, but the truth of the matter is, a balanced equation remains balanced if every coefficient is multiplied by any number you want to. And whole number coefficients aren't really required in order for it to be balanced. Even decimal coefficients and fractions could be used and lead to a correctly balanced equation in the sense that everything in there conforms to the law of conservation of mass. Okay, let's take some examples and illustrate what I'm talking about. Here's the reaction of aluminum and hydrochloric acid to make aluminum chloride and hydrogen gas. It's a very easy, simple reaction. And now, this is the smallest whole number set of coefficients that would balance that equation. You've got 2 aluminums on each side. You've got 6 chlorines, 2 times 3 is 6 on each side. You've got 6 hydrogens, 3 times 2 is 6 hydrogens on this side. So it is the balanced equation, and it's the smallest set of coefficients you could use that are whole numbers. I could go through and balance the equation by doubling all coefficients. If I did that, I would have 4 aluminums on both sides. I'd have 12 hydrogens on both sides. I'd have 12 chlorines on both sides. It's still balanced with the double coefficients. I could divide the coefficients by 10. Now, it's still balanced. I've got 2/10 of a mole of aluminum and 2/10 of a mole of aluminum, 6/10 of a mole of hydrogen and 6/10 of a mole of hydrogen and 6/10 of a mole of chlorine and 6/10 of a mole of chlorine. So it does balance. I have lost something though. There's no way this can be interpreted in atoms and molecules. You can't have 2/10 of an atom. So we've lost that relationship within the balanced equation, being able to interpret it in terms of atoms. I can't have 6/10 of a mole of hydrochloric acid either. I'm sorry, 6/10 of a molecule. But I can have 6/10 of a mole. You could figure out what that would be. Take the molecular weight, multiply by 0.6, and that would be the number of grams. So it would still work. Everything is still just fine. It will still work on every practical type of problem. But we just can't talk about it in terms of atoms and molecules, but it is still balanced. I could multiply all the coefficients by 0.135. Now, I just made that up, okay? But if I did, this is what I would get. And when I look at the coefficients, sure enough, 0.27 aluminum, 0.27 aluminum, 0.81 hydrogens, and 0.2 times 0.405 would be 0.81. And so everything still balances. Now, I could do all three simultaneously. I could double the coefficients, take that result, divide by 10, take that result and multiply by 0.135. If I did that, these are the coefficients and it's still balanced. Okay, now I know I'm beating a dead horse. I hope you all get that point. I can do anything to the balanced equation that I want to do as long as I do it to every species in the balanced equation, everyone in the reactants and everyone in the products. It will still remain balanced no matter what I do to it. Let's work a problem now. How many moles of hydrochloric acid are required to react with 0.6 of a mole of aluminum? Okay, here's my balanced equation, or 6 moles of aluminum. Now, I want this reaction to involve 6 moles of aluminum in my problem if the balanced equation only has 2 moles of aluminum. What could I do to that equation to make it look like the problem? Well, yeah, multiply by 3. If I multiplied through by 3, now look at what I've got. I've got 6 moles of aluminum reacting with 18 moles of hydrochloric acid to make 6 moles of aluminum chloride and 9 moles of hydrogen. But we just answered the problem. How many moles of hydrochloric acid? 18. See how easy that mole-to-mole stoichiometry problem was? All we did is rebalance the equation to make it look like what the problem was asking for. That's the method we're going to be using. So 6 moles of aluminum requires 18 moles of hydrochloric acid. Now, here's another one that's a little bit harder. This is moles to grams, and moles and grams. How many moles of hydrochloric acid are required to react with 5.4 grams of aluminum? Okay, now, if I look at this equation, 2 times 27 is 54. So the equation is showing 54 moles of aluminum in it, but I only want 5.4. What do I need to do? That's right, divide by 10. Now, let's divide every coefficient by 10. I get 0.2, I get 0.6, get 0.2, get 0.3. I've rebalanced the equation now, but the equation, that 0.2 moles of aluminum is 5.4 grams. So I've rebalanced the equation to make it conform to the problem. And when I did that, look at what I got for the answer. The answer said how many moles of hydrochloric acid? Right there it is, 0.6. See? I didn't do grams to moles and moles to moles in this case. 5.4 grams of aluminum requires 0.6 of a mole of hydrochloric acid. Okay, so here's the general method. We're going to calculate a rebalancing factor, what I need to multiply through by in order to make the balanced equation conform to the problem. See what we're doing? We're taking something we all know how to do, balancing equation, and we're going to change it from the balanced equation we would get to what the problem is asking. And we do that by multiplying through by what I call a rebalancing factor, RBF. Okay? The way you calculate the RBF is you take the problem quantity, whatever it is and whatever unit it is, out of the problem. This is a number and a unit out of the problem. And now you locate that substance in the equation and put it in the same unit. The equation quantity now in the same unit we used in the problem. Now, generally, we'll have this unit. We know what it is, but we want to put the problem quantity in that same unit here. Okay, so that's the general method. We take whatever's given in the problem with its unit, locate that substance in the equation and put it in the same unit that's in the problem, and then multiply everything in the equation through by that. And then to calculate the answer, you take the rebalancing factor and multiply it by whatever is shown in the problem from the equation in the unit that's in the problem. So I'm going to take this rebalancing factor, I'm multiplying it through by everything. In particular, I'm going to multiply it by the equation quantity of whatever was asked in the problem in whatever unit the problem asked it. So keep these two in mind. You might jot that down somewhere to refer back to it. We're going to be using it a lot. So the part of the problem is just getting a rebalancing factor that I'm going to multiply through the entire equation. Once I get that number, I'm going to just multiply it by one of the substances in the reaction that the problem is asking for. Okay, let's look at this. Now, how many grams of hydrogen will form from how many moles of hydrogen will form from 8 grams of aluminum? Okay, I'm looking at the problem. The problem says 8 grams of aluminum. So I'm going to put the 8 grams of aluminum in the numerator. That's what the problem said. Now that tells me I'm going to the equation for aluminum, and I'm going to interpret the amount of aluminum in grams. How much would that be? Well, it'd be 2 moles, so that's 2. And the molecular weight is 27.0 for the atomic weight of aluminum. So my rebalancing factor is 8 divided by 2 and divided by 27. That gets the same unit in the numerator and the denominator. So my rebalancing factor now is just a raw number, 0.148. That means to get this problem, I need to multiply everything in the equation by 0.148. But specifically, I'm just interested in the hydrogen. So I'm going to multiply 0.148 times the amount of hydrogen in that equation in the problem unit. It said moles. So the problem wanted moles. There's 3 moles of hydrogen shown in the balance equation. So I'm going to take that, multiply it together, I get 0.444. Okay, so you see, I'm focusing now just on the things that was in the problem. I had this and this. I could have left all the other stuff out. It wasn't mentioned in the problem. I just have it there because it completes the balance of the equation. But these are the 2 substances that are in the problem, the aluminum and the hydrogen. And my rebalancing factor, I was given a quantity. So I put that quantity in with the units and what it is. That's why I also insisted when you write down grams, don't just do G. It's G of something and grams of aluminum, because I want to know that this unit cancels this one. Okay, and then once I've got this one, I go to the balance equation to put what goes in the denominator here, and it has to be in grams of aluminum. So this is 2 times 27.0 grams of aluminum is what's shown right there by the 2Al in gram units. Divide them out, I get that, multiply through. I'm multiplying everything through by that. I get the answer I want just by multiplying that by what's shown here, 3H2 in mole units. Well, there's 3 moles. So 3 times that gives that. Okay, now what I've done is I've multiplied everything through just so you could see what that amounts, what that new rebalanced equation looks like. Now, you know, I would never teach you a method that I haven't done and tried myself. And I will guarantee you, as a chemist, as a research chemist and scientist, I always work every stoichiometry problem by the method I'm showing you. It's particularly important, say I'm doing lab. I teach labs almost every semester, well, Usually not in the spring, but most falls and summers I teach labs. And one of the things we have to worry about, we talked about it with you guys in the first lab lecture about safety and hazardous chemicals and how we dispose of them and where they go and all that stuff. Well, if I'm doing this problem, I I I certainly want to know that I'm going to get 0.444 moles of hydrogen in that, because maybe that's the amount of hydrogen I want a particular student to generate in a lab experiment involving these. Maybe the whole experiment is to make hydrogen and do something with it. And I want to know how much I'm going to get for each student. Okay, well, there you go. I got that much for each student. I know also how much hydrochloric acid I'm going to need. I can look at that. I'm going to need 0.888 moles of hydrochloric acid for every student. Now, that's going to be a lot. I might want to scale that down. But anyhow, that's I got that, and I got how much aluminum chloride. Now, truth of the matter is, aluminum is so common in the environment. I think I could dump that down the drain, and the OSHA people couldn't even find it because there's so much aluminum in our water stream anyhow. But I wouldn't. I'd put it in a waste container, and I need to know how much aluminum chloride a lab of 24 students is going to generate. So I've got a container that big, and I can put that in there. So the neat thing about this is not only do I do my problem and get the answer that I needed, I got the amount of every other thing in the reaction all at once at one calculation. I got everything all at once. So this is, for me, one of the very best things about this process is when I do these, you know, hey, it's an exercise when I do them on tests and quizzes and stuff like that. It's something quite different if you're going to be responsible for a lab and you've got to put all of those things in. I'm going to do it just like this every single time. I'm going to solve one problem and get them all, rather than, okay, well, let's see how much hydrochloric acid each student will generate. Got that? Now let's see how much hydrogen each student's going to get. And get that. And then let's do another problem. See how much aluminum chloride each student's going to get. Frankly, that's the way most of the chemistry professors would do the problem. They would do 4 problems there. 3, I guess. 3 problems in this case. To get everything I got with 1. I did 1 problem, and I got everything. So 8 grams of aluminum will form 0.444 moles of hydrogen gas in the reaction. Now, here is the one that everybody really moans about in freshman chemistry. What about the limiting reagent problems? Ooh. Hey, not a big deal. Watch. There's my reaction. We want to know how much hydrogen, how much of this, and we want mass in this case, will form from 5.85 grams of aluminum and 0.612 moles of hydrochloric acid. Now, your textbook would tell you, work 2 problems. Work this one and see how much hydrogen you would get, and then work this one and see how much hydrogen you would get. And whichever one gives you the smallest amount of hydrogen, then that's the one that governs the reaction. That's the so-called limiting reagent. It would be used up first. Well, that's all true, but it's 2 problems before you can start the problem. Okay, let's do the rebalancing factor in aluminum. We got 5.85 grams of aluminum. There it is. And the equation is showing 2 times 27. And do it like that. When you set it up like that. Don't write 54 here. If you write 2 times 27 and you work the problem and you get the wrong answer, you can go back. One of the common mistakes is to forget to put that 2 in. Or forget to put the 27, that'll make a big difference, okay? But anyhow, put them, set it up like that. That's the amount in the problem, unit given in the problem, unit given in the problem, amount in the balanced equation right there, okay? Now, that rebalancing factor is 0.108. Now let's suppose we had the other problem, the other stuff. We got 0.612 moles of hydrochloric acid. The equation is showing 6 moles. Remember, you have to interpret the balanced equation and the unit that was given in the problem. The moles of hydrochloric acid was given in the problem. So I want moles of hydrochloric acid here. There's 6 of them. There's my rebalancing factor, 0.102. Okay, I've highlighted that one because 0.102 is less than 0.108. There's the limiting reagent. We already know what it is. Okay, how do we now get the answer? We multiply through by the limiting reagent. That's the one that's going to be used up first. So when all of your hydrochloric acid is gone, you're not going to use the rest of your aluminum. You're just going to use what it took to use up all of the hydrochloric acid. And so the amount of the hydrogen that you would make in grams, it said what mass. The equation is showing 3 moles. Each mole of hydrogen gas has 2 hydrogen atoms, and the atomic weight of hydrogen is 1.008. And I'm going to write it like that. So I know I have got this coefficient taken into account. I've got this coefficient taken into account, as well as the atomic weight of hydrogen. There's my answer, 0.617 grams of hydrogen. So that's how much you would get in this limiting reagent problem. What did we do different? Well, we were given quantities to do 2 rebalancing factors. So I just tackle that first, see which one's smaller. I'm done. I got the answer now. All I got to do is multiply everything by 0.102, and that gives the amount of everything that's used in the reaction. I got it all in one fell swoop. I know there's going to be some aluminum left over because the limiting reagent was the HCl. So if I wanted to know how much aluminum got used, I've already got the answer, 0.102. When I multiply that by 2, I got 0.204 moles of aluminum. Now, if I wanted to know how much excess I have, I take 0.204, multiply it by 27. That's how much got used. I had 5.85 up here, subtract the 2, that's how much aluminum is still left over when the reaction is done. So you see, that's about as complex as you're going to get in chemistry problems. And we've got the amount of everything all at once with one calculation. You know, I think that's cool. Okay. 0.585 aluminum and 0.612 moles of hydrochloric acid will form 0.617 grams of hydrogen. Okay.
Dr. Pierce,
Yes.
real quick. So with 0.108, are we just not doing anything with that in that equation?
We don't need it because it's still going to be some of the aluminum left when that reaction is over. The hydrochloric acid is going to get used up first, and so the 0.108 we don't need. That was just, we had to calculate it to see which one was limiting. And when we compare these two numbers, 0.108 is larger than 0.102. The smaller number of your rebalancing factors is the limiting reagent for the reaction. And that's the only one you need. Now, like I said, I know how much aluminum got used, 0.204. So 0.204 times 27, that's how many grams of aluminum I will use. If I subtract that from the 5.85, that's how much aluminum is left over. So sometimes they'll give a problem like that and think that made it a lot harder because now you got to figure out how much of the excess reagent got used. Well, it's not harder for us. We got it when we multiplied by 0.102. We got the amount of aluminum that was used, and we just subtract that from what we started with, and that's how much is left over. Now let's look at a little more complex problem. Now this is a biggie. And this is a reaction. Yeah, I've been known to use that equation as a stoichiometry problem on old exams. Okay, so we take hydrogen peroxide and potassium permanganate, acidify it with sulfuric acid. It'll make manganese sulfide, manganese 2 sulfide, potassium sulfate, water, and oxygen. So it'll generate oxygen in this reaction as well. And this might be a useful one to go through and see what got oxidized and what got reduced. You might want to try that sometime. It might be fun. Okay. All right. Now, let's see. What mass of oxygen gas will form if 6.75 grams of peroxide, so we got a rebalancing factor. Let's do it. 6.75 grams is given in the problem. How much is the equation showing? 5 moles. And the molecular weight is 34. 2 times 16 is 32, and 2 times 1 is 2, and 32 and 2 is 34. It's 34 grams. This is what's shown in the problem in grams. This is what's shown on this is the problem. This is the equation in the same unit as the problem. We divide it out, we get 0.039. So the rebalancing factor for the reaction with the hydrogen peroxide is 0.039. We're going to have another rebalancing factor. Okay, we've got an amount of potassium permanganate given. How much is it? It's 12 grams. And how much is shown in grams of this? It's 2 times the molar mass of this. And the molar mass of potassium permanganate, if you figure it up, is 158. There's 2 moles, so it's 2 times 158. Do your math. You get 0.0380. Okay, this one's winning so far. This is a smaller number than that one. But we got another rebalancing factor, and we had 0.25 moles of sulfuric acid. And the equation is showing how much sulfuric acid? 3 moles. Now, why didn't I put 3 times 98 as the atomic molecular weight of this? Why didn't I put that there? Because this isn't grams. This is moles. Whatever, if this is moles, the equation, you have to interpret the equation in moles. If this is grams, you have to interpret the equation in grams, and so forth. We do the math. There we got 0.0833. Oh, okay, this guy won already. So I've got my rebalancing factors. I know the one that's limiting everything. I'm not going to do what the problem says. I am absolutely not going to take 6.75 grams of hydrogen peroxide, convert that to moles, and then take that and convert to moles of hydrogen, what does it ask for? Well, oxygen. Convert that to moles of oxygen, and then convert that to grams and get one of the answers. Then go take the 12 grams of potassium permanganate. Work the problem through again. Take the 12 grams of permanganate, convert it to moles. Take the equation, convert from moles of permanganate to moles of oxygen, and convert moles of oxygen to grams and get the second answer. And then do the third problem. 0.25 moles of sulfuric acid, take that moles and convert to moles of oxygen, and take the moles of oxygen and convert to grams and get that answer. I'm not doing that. That's going to take half the period. This takes literally seconds. And you know what I do? Now, if I were, I'm showing you these results in here, but if I were doing this problem for real, I would have these things on my calculator screen. I would do this first calculation, push equals, and it would show 0.0397, whatever the other values were. Then I would go to this second one, do this calculation and push equals, and that would show on this line, it would show 0.0380, but the 0.0397 would still be on my screen up there. And then I would take this and do the calculation. It would show 0.0833. And if I'm lucky, all 3 of those numbers are still on my calculator. And if they are, I know what the limiting reagent is. Now, honestly, if your calculator allows you to go back up on the screen. You can go back up there to this one and get this number all by itself. You can pull it up right now and finish the problem. For me, I can't go back up past the line I'm on. I can correct on the line I'm on, but I can't go back to the other one. So if I've located this as the rebalancing factor, in order to put it in my register and not have to do a copy, and you already know, half of the time I'm going to write down, instead of 0.038, I'm going to write down 0.083. I don't know, it's weird. But I won't make that mistake if I redo that calculation and put it in the answer register. And then what do? Okay, you've got the answer is the limiting reagent rebalancing factor multiplied by the oxygen in the problem unit. It's grams. So it's 5 moles. 5 moles. Each mole of O2 has 2 oxygen atoms. The atomic weight of oxygen, effectively 16. That's the real value, 15.9994. Okay, so here's my answer. I've got 6.08 grams. I've got that answer. See how quick that was, how easy that was? You almost have to try to mess this up, okay? And to me, stoichiometry is no big deal anymore. In fact, if I were taking a test, I'd look for the stoichiometry problems first. Now, here's what you get when you take that rebalancing factor, 0.0380, and multiply it through by everything shown in the equation. Here's your new coefficients. And again, this gives me 0.190, gives me the number of moles of O2 that is the answer to the problem, 6.08. But it gave me the amount of everything else in the reaction at once. And now, if I wanted the amount of all of the other things that were in excess, if I want to know, well, how much potassium permanganate is going to be left over? Well, there's how much is used. Multiply that by the molar mass. That'll be the grams. And if I go back up here and subtract that from 12, that's how much potassium permanganate is still left over. Okay? And what was the other? Sulfuric acid, I guess. And again, if I know that many moles and I had that many moles, well, I can subtract this number from that one. That's how much is left over of the sulfuric acid. So I've got everything all at once. If I'm a lab teacher, I have generated a whole mess of very dangerous chemicals. Manganese is a toxic metal. That has to go in the toxic waste. So I've got that. I know how much sulfuric acid I have to use. I know how much of the potassium permanganate I've got to use. I've got everything all at once in one calculation. So that's what I'm going to do. Now, I'm going to convert all of these over and show you how much got used up. Okay, and how much was formed and so forth. Okay. Oopsie daisy, previous. I want to back that up. So here we go. This 0.190 is 6.46 grams of the peroxide equation. We had 6.75. If I subtract 6.46 from 6.75, that's how much excess is left over. It turned out the potassium permanganate was the limiting reagent, but I can see it here. When I'm going to use 12 grams of potassium permanganate. The problem has 12 grams. How much is left over? None. All of it's used. And then I'm going to get 11.2 grams of sulfuric acid, and the number of moles was 0.114, and I do 0.250, so subtract 0.114 from 0.250. That's how much of this is left over. How much of the manganese sulfate would I generate? 11.5 grams. I'm guessing if I'm going to do this lab experiment, I don't want to generate 11.5 grams of hazardous waste from all of my students in my lab. And typically in the fall semester, we have roughly 20 sections of freshman chem lab. And that would be a whole mess of of manganese 2 sulfate that you'd have to get rid of. That'd be pretty expensive. I'd probably scale that down maybe by a factor of 10 if I could get it, if that would be okay for the reactions we're doing. Okay? And so forth. I've got all of them. Now, we said this has to conform to the law of conservation of mass. So if I add 6.46 to 12 and 11.2, I better get the same number that I get with 11.5 plus 6.62 plus 5.48 plus 6.08. That would show that it still obeys the law of conservation of mass, even when scaled to a different set of coefficients than what was used in the balanced equation. Okay. Now, how many total moles of product will form if 6.75 grams of sulfuric acid is reacted with 12 grams of potassium permanganate and 0.25 moles of sulfuric acid? I think that's the same problem. But now I want to know how many grams, how many moles of product of all the products. There's 2 moles and 1 mole and 8 moles and 5 moles. How many total moles would I get? Now, I'm not going to do this way the problem implies and the way the book would tell you. Probably work 5 different, 1, 2, 3, 4 different problems and then add the answers together. But you've got 3 possible limiting reagents. So there's 3 different ways to do 4. That's 12 different problems you might have to work doing it the way the books would tell you and the way you probably learned in high school. And you'd be here next week. All right. All right. With a limiting reagent, we determined from the previous problem, and the rebalancing factor was 0.0380. Okay, so what am I going to do? Okay, I'm going to just multiply by the equation amount in the problem unit. Well, there's the equation amounts. What is the problem units? Moles. 2 and 1 and 8 and 5. That's 16. So there's 16 moles shown in the balanced equation. What I'm going to get in my problem is the rebalancing factor times 16, 0.608. So the total number of moles, if you add all of those new coefficients up, it'll total 0.608. We got it all in one problem. Okay. Now, here's a checkpoint, and let's work through that one. And let's go over so that you can see this and I can see the problem. And it says iodic acid. Okay, and I didn't tell you what that was. That comes from, it's the hydrogen compound, aqueous hydrogen compound of iodate. Iodate would be like chlorate. So IO3 minus is iodate, and HiO3 would be iodic acid. And we're going to react that with hydrochloric acid. And we're going to form iron. Oh, wait, I left off my iron. Oh, I had hydrochloric acid, but I got another reactant up here. It's iodic acid, iron 2 iodide. So that's iron is a +2, and iodide is -1. So I'll need 2 iodides. So that's the formula for the reactants. Iodic acid, iron 2 iodide, and hydrochloric acid react to form. And let's see, to form iron 3 chloride, so that's going to be Fe in the +3 state. So chlorine is a -1, so I'll need 3 of them. And iodine monochloride, it's ICl, and water, and H2O. Now, we got to write the correct formulas and balance the equation and do the limiting reagent. Oh, gee, I don't really want to balance that equation right now, but we've already done it. Okay, I will do it. All right, let's see what we would start with. Oxygen is by itself on each side of the equation. Hydrogen's in more than one. I can't do hydrogen. And iodine is in two different places. I can't do iodine. Can't do hydrogen. I could do chlorine. No, I can't. Chlorine's in two places in the product. So the only one I can start with really is oxygen. To balance oxygen, if I put an A right there, I would need a 3A over here. And that would balance oxygen, sets up hydrogen. That balances oxygen, sets up iodine and hydrogen. Okay. I think I better transfer this to another piece of paper. And turn it the other way. So let's do that down here. Plan ahead next time, Earl. Okay, we've got an A, we've got H with a dot over it, we've got iodine with a dot over it, we've got oxygen, 3 of them with a check mark. We've got HCl, I have not done anything with. We've got FeI2 that I've not done anything with. We've got FeCl3, and I've not done anything with it. We've got an ICl, and we've got a 3AH2O. We've got a dot over the hydrogen and a check mark over the oxygen. So does that looks good to me.
Dr. Pearson,
Yes.
you forgot the 2 on the iodine for iron.
I've got what now? Oh, FeI2. Thank you. I copied that wrong, didn't I? Yes, I did. Okay, thank you for catching that. It would have messed me up big time later on. All right. Now, we're looking now at the next element I'm supposed to balance is one of those that's dotted. Now, I can't do iodine for sure because I need a coefficient here and here to balance iodine. We only can affect one coefficient at a time. So the only one that makes sense to do is try to do hydrogen. Well, over here, I've got 3 times 2. I've got 3A times 2. I've got 6A. I've got 1A hydrogens here. How many more do I need? 5A. So I need a 5A right here. That'll balance hydrogen, sets up chlorine, and now hydrogen is balanced. So 5A plus 1A is 6A, 3 times 2A is 6A. So hydrogen is balanced. I'm done with water over there already. Now, the elements that are left are chlorine, and I can't do chlorine next. Why? Because I need a coefficient here and here. Can I do iodine? No, I need a coefficient here and here. So I can't do any of the elements that are dotted with the A variable. What do I do next? That's right, I go to B and I balance something that's not dotted, and that would be iron. So I put a B there to balance iron on this side. That means I need a B right there to balance iron on this side. So the iron is balanced, chlorine is set up, and chlorine is set up. I need just this one coefficient. So let's see, can I figure out what that coefficient would be? Let's look at iodine. I've got A iodines from here, and I've got 2B from here. So I need a coefficient here of A plus 2B. Now that checks off iodine, dots chlorine. Now, if you look at this, I've got a coefficient here, 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 I've got a coefficient here. The equation is balanced, but I don't know what A and B is. So let's now I'm going to balance chlorine and force it to balance on the left-hand side for reactants and products for chlorine. Okay, on the left-hand side, I've got 5A. That's the only one that's got chlorine on the left-hand side. So that's got to be equal to whatever is showing on the right-hand side for chlorine. There's 3B from here. And chlorine here, there's A plus 2B of those. And nothing else has chlorine in it. So I've got 5A is equal to A plus 5B. Subtract A from both sides, I get 4A equals 5B. And so A is equal to 5 and B is equal to 4. Let's see if this works. So A is 5, so I'm going to write 5 HiO3 plus 5 times 5 is 25 HCl plus B is 4 FeI2s and B is 5 FeCl3s and let's see, 5 plus 2 times 4 is 8. 8 and 5 is 13. 13 ICl. And the water, I've got 3 times 5 is 15 waters. Ran out of space even on that one. Okay, but anyhow, we got it balanced. And so the equation is balanced, and I do remember the coefficients after I get through, so you can check them, but I'm pretty sure that is correct. Now, let's do this problem. We want 5 grams of each reagent. So I'm going to say I've got 5 grams of this. I'm going to show you the way I set it up that makes the rebalancing factor calculation easier. So I had 5 grams of this. I've got 5 grams of this and 5 grams of this. And I'm not worried about sig figs right now. Okay, but now, what do I do? I've got 5 grams here. The equation is showing 5 moles. Now, I've got to get the molar mass. Hydrogen, I remember, is 1. 1.01, I think. Iodine, I believe, is 127, but I'll look it up just to be sure I don't screw it up. Okay, so iodine is 126.9 something or other. I'm going to use the 127 that I remember. That'll be the 3 significant figures, and it looks like our problem had 3. So it's going to be okay. And of course, oxygen is 16. And chlorine, I'm going to need it. I'll put it up here. It's 35.45, I think. Pretty sure it's right. Wow. I'm going to have to get new glasses. I already know. Yep, that's right. 453, I think is it. And iron, 55.85. Okay. So iron, 55.85. Okay. Now, so it said what mass of iodine monochloride? So how much of this in grams? Okay, so I've got all my setup. Let's go through now and put in. And you see, I could look at this problem and read off the problem. What mass of iodine monochloride forms from 5 grams of each one of the reactants? That's the problem. I can see it right there the way I've got it set up. Now, the rebalancing factor has the equation quantity in grams. So I need the molar mass of HiO3. So I'm just going to do that on my calculator. H is 1.01 plus iodine is 127 plus 3 times 16. I get 176.01. Okay, so that's the amount of this. Let's do this one, have it all set up. 25 moles, so it's 25. In grams, I need the molar mass. That's 1 plus 35.45 is 36.45. And now 4, it's grams, so it's 4 moles on FeI2, so its iron is 55.85 plus 2 times 127. That is 309.85. The iron 3 chloride, there's, oh, no, that's product. I don't need that. It wasn't in the problem. So, and water, I can ignore that. I just need the one for the iodine monochloride in grams. So I've got 13 moles. Iodine monochloride, iodine is 127, and chlorine is 35.45. That's 162.45. Okay, now I've got everything set up for, there is the problem. There is the equation amount in the problem units down here. I just need to divide these all out to give me my rebalancing factors. So my rebalancing factors, it's going to be 5 divided by that. So 5 divided by 5 and divided by 176.01, I get 0.00568 and a whole bunch of other digits. Now let's do this one. 5 divided by 25, 5 divided by 25, and divided by 36.45. Oopsie daisy, made a mistake. 5 divided by 25. 5 divided by 25 divided by 36.45. Okay, this is 0.00548 6, a whole bunch of other digits. 5 divided by 4 and divided by 309.85. That's 0.00403 and a whole bunch of other digits. Now I've got my rebalancing factors all calculated. It's 0.00568, 0.005486. This one's smaller than that one. And 0.00403. This one's smaller than that one. So the smallest one of the three is this one. So the iron 2 iodide is the limiting reagent in this reaction. So how much product do we get? So my answer is going to be equal to my limiting reagent rebalancing factor, 0.00403 and digits, times what's shown under my question mark here is 13 times 162.45. Now, I'm sure you can't read my screen, but the last number I have on my screen is this number, the limiting reagent rebalancing factor. So for me, the easy thing now is just going to be say, okay, I want to take that and multiply it by 13 and multiply it by 162.45. And I'm going to get 8.5196466603. That's what I got off my equation, my computer or calculator screen. And I'm looking back, all of these numbers were 3 significant figures in the given problem, 5.00 grams. So I want 3 sig figs. It would go to right there, wouldn't it? No, I'm sorry, 3, 1, 2, 3. So it'd be 8.52 would be the way I've reported. Okay, now that's pretty good. Okay, now it has one more little caveat to it. In real life, you would probably, if you put this together, I doubt anybody would be good enough at the chemistry to get exactly 8.52 grams of product. Most of the time, there's going to be some losses and some errors and some side reactions you didn't know about and other things that can happen in there. And your yield is usually less than that. So if I knew, for example, the yield in this problem, it tells me the yield is 87.5%. So I need to take that into account and say, okay, if I'm only going to get 87.5% of this, what would I actually get? So I'm just going to take this number and multiply by 0.875. So times 0.875. This is what's called theoretical yield. Theoretical yield, multiply by that, and I would get times 0.875. I would get 7.45 grams actual. So my actual yield is only going to be 7.45 grams in this reaction that's 87.5% efficient. The theoretical yield would have been 8.52. Now, this problem has just about everything I can think of to throw at you. I couldn't come up with an equation much more complex than that one. But I want you to notice the format I did that saves a lot of time. And that is, you put your problem amounts here above the balanced equation, and you put the equation quantity in the same unit as the problem right under each substance. By setting it up like this, you've set it up to calculate your rebalancing factors. This divided by this and this divided by this and this divided by this and this gives you those 3 rebalancing factors. And like I said, most of you, suppose, I think I remember, I put the order reverse back up there from the problem, the way they read. I put this one after this one. It turned out that was a good thing because the last number I calculated turned out to be the limiting reagent. If I put it in the other way, that one would have been here. I'd calculated it second, And this one would be over here, and I'd have calculated it last. Well, my screen, I can't get back up there to this number on it. So what would I do? No big deal. I'm just going to put 5 divided by 25. I know this is a limiting reagent. I know what the number is. I wrote it down here, But I would take this, divide by this, divide by this, recalculate that rebalancing factors so it shows on my screen. And then I would take that answer times 13 times whatever's under the question mark, wherever it is. In this case, it's 13 times 162.45, and that gave me my answer. So in most of your cases, you've got newer calculators than mine. If that number's up there, I don't know, I think in some of them it can even go to what's already scrolled off the screen, but mine won't even do 2 lines. So I have to do it that way. And rather than copy down the rebalancing factors and write them down and then enter them again and do all that kind of stuff, I'm never going to do that. I'm just not going to do that. Now, let me warn you, you're in Gen Chem 1 with me. If you take Gen Chem 2 this summer, it won't be with me because I'm not teaching second session. If you took it in the fall, I probably won't be teaching it. So chances are pretty good that whoever is teaching Gen Chem 2 will never have seen problems work the way I'm showing you. And I honestly seldom write anything on the paper when I'm doing my own problem except the final answer that I want. I don't want to forget it. And then once it's gone off my computer screen, I could forget it. So I don't write anything down on the paper except the final answer. All of my stuff is done inside the calculator. You could do that too, but let me warn you, if you do that in Gen Chem 2 and they don't know you had me, and it's not here at MTSU, most of the faculty at MTSU know how I teach it, and they might be a little more forgiving. But if they've given you a stoichiometry problem to work from scratch, they're expecting to do partial credit for stuff. If you do it this method and then you mess up somewhere and get a wrong answer and write the wrong answer down, you want to get no credit at all. So you might want to jot down a few steps if they give you a work from scratch problem in Gen Chem 2. They might not recognize what you're doing, but if you put these factors down, for example, if I'm setting up this problem and let's suppose we just had this one amount that was the limiting reagent, this one. If you set up on your paper 5 divided by 4 divided by 309.85 times 13 times 162, they'll see that and recognize that gets the correct answer. The only thing that would need to be done to work it the way they're used to seeing it is move that 13. I mean, this factor over, no, this factor from the denominator of the second factor over to the first one. That was my dream. I saw that when I moved that number over, I was getting something I could multiply through the whole equation to get the answer. And that's where that came from. Now, I still believe it's the very best way to do stoichiometry and the very least likely to make mistakes. And I've had students years after they had me in class contact me and say, Dr. Pearson, I need a refresher on how you did stoichiometry problems. I know it was a lot easier and I've forgotten. So I've gotten back to them even years later. People do forget if they don't use it. But it's an easy way to do stoichiometry. It makes that part of chemistry a lot easier to actually do. While I'm thinking about it, this percent yield. Now, if you're looking at a product and you know what the percent yield is, Or if you know how much you actually get, the actual divided by the theory is going to be the percent yield. So if it asks you, it tells you that when you got through, you got 7.45 grams of iodine monochloride, what was the percent yield? Well, you would work it through the same way we did. You would get this 8.52 is theory. So if you take the actual 7.45 and divide by 8.52, multiply by 100, that gives you the percentage. So that's how you would do it. You would take this into account last. And that's exactly what I would do. Suppose, for example, I'm trying to make the iodine monochloride, and I want to have in my hand 7.45 grams of it. And I say, okay, well, how much of some reagent would I need? How much of iodic acid would I need in order to make 7.45 if the yield is only 87.5%? Well, what I'm going to do is I'm going to take the 7.45. I'm going to take that divided by 13 divided by 162. That gets my rebalancing factor. I'm going to multiply that by 5 times 176. That gets the amount of this I would need to use if this was 100% efficient, but it's not. So once I get this amount over here, if I divide by 0.875, then that will give me the amount of that stuff I'd need to start with. So I can calculate how much of this I'd need to start with, and in this case, it would be a little more than 5 grams. So we can figure out what it would be once we know what we want. So again, what you're going to do is work the problem through theory first, and then take the percent yield into account. If you're looking at a product, how much product would you form actually, then you're just going to take the theory and multiply by the percent yield. But if they ask you how much of a reactant do you need if the reaction's only 87.5%, I'm still going to work it through like it was 100%. But when I get my answer, instead of multiplying by 0.852, 875, I'm going to divide by 0.875. And that will scale things up so that you'll have enough stuff to start out with that when you get to the end and multiply by 0.875, you're going to get this one. That makes sense. If you're doing percent yield and it's dealing with a product, you're going to multiply by the yield. If it's a percent yield and it's a reactant, you want to know how much reactant you have to start with, then work it as if it were theoretically correct. Theory, it was 100%. Once you get it done, then divide by your percent yield, and that will scale up high enough so that when you get to the end, you'll get the amount of product you actually really wanted. So that's the way you can manipulate this. Now, word of caution. I know I think it looked kind of simple to you when I did it, when I worked through these problems. It was strange to you, and some of you are sitting back there thinking, yeah, I don't have to do that. I can do grams to moles, moles to moles, moles to grams. I can always get it right. Yes, you can. You sure can. Try working 2 of them on a 30-question test in 55 minutes. There's 2 of them on your exam. So if you're planning on that method, I suggest to you, you wait and work those 2 problems last because you're going to run out of time. If you know my method and you practiced it and you can work the problems, you know, it's a little bit math involved, but we did a lot of stuff here we wouldn't need to do. In a typical problem where you got 1 reactant and 1 product, I'm just going to deal with those 2 things. Say if I want to know how much of iodine monochloride I would get from 5 grams of iodic acid, I'm only going to take the 5 iodic acids and the 13 ICLs, and that's the only 2 things I'm going to put down on my paper. I'm going to put the amount of one that's given divided by the equation amount in the same unit, and that's going to be my rebalancing factor. And then once I get that, I'm going to multiply by the coefficient under the numbers under what was asked to calculate. In this case, the iodine monochloride. So you can work these problems very quickly. And if you keep your head about you, you're really not very likely to make mistakes. If you go through that old method, chances are pretty good you'll make a mistake. You might not. You might be really good at it. But I still think you would be quicker and better if you're ever going to use chemistry for anything. It's probably going to be a stoichiometry somewhere, sometime. And if you put in a responsibility where you have to know how much of everything you're using, believe me, if you're using silver nitrate in a solution and your boss catches you using 3 moles of it, you better have a good reason. That's going to cost him several $1,000 for that bottle. So you better know how to use 1 gram out of that 5-pound bottle. All right. So, okay, enough for that. Let's escape out of here. And now, this is going to be a place I think we're done. Let me look and see for sure. Yeah, yep, that's the last slide. So we've finished segment 11 now. I'm going to pause the recording and I'll pick up in just a few minutes recording. Now we got it. Okay. Yeah. For the rest of the period today, we will work on the practice exam for this unit. Let's see if I can make it a little bit bigger for you to see. And I hope that you have a copy of the practice exam with you. It'll make things a lot easier if you can follow along with me like that. I will go over to the camera and work the problems out, especially all the mathematical ones. The ones that we can do without it, we might work without the camera. But okay, number 1 is we're trying to find the bond angle. So we're looking for the bond angle in a bunch of molecules. Now, what that should tell us is, now, if we look at all of these molecules, they're all central atom molecules. The first one is ClF3. The second one is SbBr6-, PCl4-, and BeCl2. And we're going to get the angle of each of those compounds. And that essentially means we need the VSEPR notation. AXMEN. Let me shut my door. Okay. So we need to find the VSEPR notation for each one of them. I'll do one of the wrong answers and the correct answer. It says B is SbBr6-. Okay, let's see what that, we got to get the number of valence electrons. Antimony is in group 5, so it's 5 valence electrons. We've got 6 bromines, and they're in group 7. And we've got a negative charge, so we're going to have to add 1. So 6 times 7 is 42, plus 1 is 43, plus 5 is 48. So we've got 48 valence electrons. So I'm going to take the 48, I'm going to divide it by 8. That's a 6. 48. Remainder 0. 0 divided by 2 is 0. So this molecule is an AX6 molecule. That is octahedral, 6 things. M plus N, 6 plus 0 is 6. So that is an octahedron. All the bond angles in an octahedron are 90 degrees. So that's not the correct answer. We're looking for one with the angle is 120. There's a 120 degree angle at it. Let's do C. That's supposed to be the correct answer. So I've got PCl 4 minus. Phosphorus is also in group 5, so there's 5 valence electrons. We got 4 chlorines. Chlorine's in group 7. And we add one more for the charge, 28, 29, 34. So this is 34. Divide that by 8. It will go 4 times, 32. And 2 divided by 2 is 1. So this one is an AX4E. So 4 plus 1 is 5. So that is a trigonal bipyramid. I'm going to put it over here. Trigonal bipyramid has the trigonal part and the axial part. It has one lone pair of electrons. The lone pair of electrons go into the equatorial plane. So phosphorus is going to be here. There's going to be chlorines on each one of these positions. And then, of course, 6 electrons around each one of them, da, 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 da. And there are 2 kinds of bond angles. There's one, that's 180. There's a bond angle right there. That's 90. Yeah, 90. And there's this bond angle right here. That's the one we're looking for. It's 120. So this molecule has a 120 degree bond angle. And actually, there's good practice for all of those that are in there. I would tell you about BeCl2. You don't even have to do the octet, the formula, and my guess is it wouldn't work because beryllium can't have an octet either. So beryllium is in group 2, but those compounds form, those elements, if I'm doing the ball and stick model we talked about, Tinker Toy model for the atoms, beryllium has 2 bonding sites. It has 2 valence electrons, it has 2 bonding sites. They're opposite each other. So BeCl2 is going to look like that. And that's all the electrons it's going to have. So its shape is going to be linear. Now there are resonance structures that you could draw. You could put electrons in and you could get a structure that would work with an octet around beryllium. Beryllium, that would probably not be the most likely resonance structure. That's going to come up in the next unit, how to determine that. All right. Now I have to screen share again. Okay, yeah, let's go on to number 2. What is the hybridization of the central atom in BRF3? Well, now, BRF3, we're going to do it the same way we would do, we did the others, because we have to get the VSEPR notation to get hybridization. So let's, so we're looking at the hybridization in BRF3. Okay, well, bromine is in group 7. And we've got 3 fluorines that's also in group 7. So 4 times 7 will be 28. We have 28 valence electrons altogether. If I take the 28, divide by 8, that's 3, and 24, 4 remainder, divide by 2, I get a 2. So it's an AX3E2, and 3 plus 2 is 5. So I've got to get hybridization to accommodate 5 bonds, 5 pairs of electrons. S, 2, 3, S, P, and 1, 2, 3, 4, 5 d orbitals. I need 1, 2, 3, 4, 5 of them. So it's going to be sp3d or dsp3. Either one of those would be correct. And the correct answer is D. Okay. I'm going to read the next problem rather than show it to you. And it's also using the same molecule. We want the molecular shape, not the electronic shape, of BRF3. The electronic shape we've already determined is going to be trigonal bipyramid. But we want to see what the electronic shape looks like. So this is number 3 now we're doing, electronic shape. BRF3. And we've already calculated it. So I'm going to assume that we got it right. Here's the danger though. If I miss number 2, I'm going to miss number 3. So I want to be careful, but I'm pretty sure this is right. It's an AX3 E2. 3 and 2 is 5. It's trigonal bipyramid, so I can draw my trigonal bipyramid shape. Now it's got 2 lone pairs on it, and they go in the equatorial plane. To make it easier to see what the molecular shape is, I'm going to put them in these 2. They would both go in the equatorial plane. So I'm going to have bromine right here, the 3 fluorines here. Now I'm not showing the lone pairs around the fluorine. There would be 3 lone pairs around each one. But this is the shape. And now if I want to ignore the lone pairs on the central atom and see what does that shape look like, it's the letter T. So it's a T-shaped molecule. And that is answer C on the exam. Now, the fourth one is the number, how many is unique, I'm going to underline that, unique resonance structures how many unique resonance structures for O, N, O plus. Okay, so again, let's see what the bonding is going to look like. Oxygen's in group 6. Nitrogen, that's a nitrogen, is in group 5. Oxygen's in group 6. And I'm going to subtract 1. So 6 and 6 is 12. 5 would be 17. Minus 1 would be 16. So I do my math. Divide by 8. I get 2. 16. I get a remainder of 0. 0 divided by 2 is 0. So this is an AX2 type. Kind of expected that. But the important point is there are no lone pairs. So let's do our structure. We got oxygen, we got nitrogen, we got oxygen. We have 2, what we call the sigma bonds, 2 bonds holding it together, that we expected. I cannot put any lone pairs on nitrogen because the math said not to. Don't follow the book's method. Do what this says. It says none. But I do need an octet on this molecule. I could do this in 2 ways. I can put an extra bond here and here. I need 2 more bonds on nitrogen. I've got to have 8 electrons. That's going to be 4 bonds altogether if I can't put lone pairs there. So this would represent one of the possible resonance structures. Okay, now there's another way to do this. I'm going to do it right here. We got some white space. And we started out with this structure. but I have to put 2 bonds. I could put 2 bonds right there. Now that still gives me 2, 4, 6, 8, 4 bonds onto nitrogen. I would have a lone pair here. I would have 3 lone pairs here. Now, if you add all these up, I didn't show it, but I should have. They're all positive. So it's a positive ion. Okay, but now, so I've got this resonance structure, which definitely differs from this one. Describe them, and you can see they're different. What does this look like? Well, it's got a single bond between nitrogen and oxygen and a triple bond between nitrogen and oxygen. What's this one? It's got a double bond between nitrogen and oxygen and another double bond between nitrogen and another oxygen. That's a description. Those 2 descriptions are not the same. Now, that's why I underlined unique. There is another resonance structure here with the triple bond on this side. Now, how would I describe this one? Well, it is a molecule or an ion that has a triple bond between nitrogen and oxygen and a single bond between nitrogen and oxygen. That's exactly the same description we used up here. A single bond and a triple bond. This has got a single bond and a triple bond. And in fact, if you think about it, if I took this first one and just flipped it over, it would be this one. So this is not unique. These are resonance structures. There's a total of 3 of them altogether. But this one is not, these 2 are not unique. There's only 2 unique ones, this one and either one of these. The other one is symmetrically equivalent to this one. Now, we don't need to go there, but if I'm expecting the what the real structure would look like, it would be 2/3 like this and 1/3 like that, because the 3 resonance structures are there, but these 2 are going to average together to make one unique one, and this one unique one. So there's only 2 unique answers, and that is response C on number 4. So that's correct. All right, let's look at number 5. Okay, again, whoops, I'm supposed to be at number 5. Yeah. Okay, I've got a molecule, and number 5 says I want to draw the 3D structure of this molecule. It's written like H2, C, C, H, C, N. Now, the first thing I'm going to do is take care of that hydrogen. That hydrogen does not belong in the middle of a molecule. You cannot do, here's the rules. Hydrogen has to have 1 bond only. Carbon has to have a total of 4 bonds. Now, they can be arranged lots of ways. I could have 2 singles and a double. I could have a single and a triple, or I can have 2 double. But I have to have 4 bonds on carbon total. But that hydrogen can't be there. Now, the rule is the hydrogen is going to belong to the element to its left, except in this case, it's obvious it has to be going this way, but it's not going to be HHC, HHC in a line. You can't have an hydrogen in the middle here. So taking all of this into account, I can put the 2 hydrogens onto that carbon. That's where they belong. I've got this carbon, but it has a hydrogen on it, so I'm going to put it down here. It attaches to this carbon, and that attaches to that nitrogen. So I've got the hydrogens now where they belong. I've not got the bonding correct. The next thing I'm going to do is, what does nitrogen look like? Nitrogen has to have 1 lone pair and 3 bonds. Now, it could be a lone pair and a single and a double. It could be a lone pair and a triple, or it could be a lone pair and 3 singles. There's lots of different ways I could do it, but the one thing that's important is it must have a lone pair. So I'm going to put them in first right now. Now, okay, now I've got the basic structure done. Hydrogen is good. I'm going to start at the left and go right. It doesn't matter, but I just more comfortable doing that. That way I'm less likely to skip something and miss a consideration that would be important. Okay, so that hydrogen's okay, that hydrogen okay, that carbon's not. It's got 3 bonds. Hydrogen can't have 2 bonds, so I can't put a double bond there. It's got to have 4 bonds on carbon. The only place I can put the other bond is over here. And do you remember what we call these kinds of bonds? When I put through these first set of bonds before I put that one in, those were all what we called framework or sigma bonds. And there's 1, 2, 3, 4, 5, 6 of them in this molecule. Now I'm putting in extra bonds. Those are called pi bonds. Now, when I'm to hear these atoms work, now carbon works. 1, 2, 3, 4 bonds on that carbon. How about this carbon? 1, 2, 3, 4. That one's okay. The hydrogen's okay. That carbon's okay. So what about this guy? No. That guy only has 2 bonds. He needs 2 more bonds. I can't put any bonds over here, because if I put a bond over here, I mess up that carbon. It's already good. So I can't put 5 bonds on that carbon. The other 2 bonds then have to go to the nitrogen. Now that fixes that carbon. 1, 2, 3, 4 bonds on that carbon. But look, it also fixed nitrogen. 1, 2, 3 bonds and a lone pair. Nitrogen's good. That's the structure that all of these questions relating to this molecule would relate to. Now it says, I want to know the VSEPR of the middle carbon atom in this molecule. Well, that would be this guy right here. Know the 3D structure and what is the VSEPR of the middle carbon atom. That's the question in the problem, number 5 on the quiz. So I'm looking at this one, and I'm going to call that my A atom. Now, how many other atoms are attached to it? And we're counting atoms. There's one right there. There's one right there, and one right there. It's got 3, so it's an AX3. Now, are there lone pairs on that one? No. So it's just AX3. And that is response D on that number 5. Now, number 6 uses the same molecule, but number 6 is asking for the C bond angle. And that's pretty good because we just got the VSEPR notation for this one is AX3. And I've got to put my arrow up. I'll put my hydrogen up here. It's got a hydrogen attached to it, and it's got 2 carbons attached to it. So that's what it looks like. Now, the way I've got it on here, the carbon to the left is bonded with a double bond, but that's okay. So this is the structure though, but it's AX3. That's what's important. What I'm going to do now is draw what AX3 is. That's trigonal planar. 3 things attached are in trigonal plane. There's 1 carbon here. This is going to actually be the double bond to this carbon. This is going to be a hydrogen, and this is going to be the other carbon that's got the nitrogen on it. So what is the angle for AX3? All the angles are 120. This one is 120, and this one is 120. So if the problem had said, what is the HCC angle, or the CCH angle, or the CCC angle? The answer is always the same. It's 120, because that's the hybridization at that carbon causes a trigonal planar shape, AX3. Okay, so now that's got that answer. And we've had 3 problems on this same molecule. And I told you in class, I do that to save you time, but you can screw up the first one and miss all 3. So be very, very careful that you got your structure right when you're using this molecule over and over again. So just look on the test. And by the way, the questions will be in different orders, so they may not be in the order we've got them here. These 3 problems might be adjacent to each other, but they might not be. They may be somewhere else. And D2L does some scrambling in exams as well. All right, so number 7. How many different molecules or isomers can exist for SCl3F3? Well, I'm going to jump ahead since we've done it all over. This is going to be AX6. So it's going to be a XYZ coordinate system. Okay, so this one is coming above the paper and this one below the paper. So the sulfur is going to be in here. Now, I'm not going to just go in here and say, my goodness, I'm going to try to put all 6 of these things at once. No, we're trying to figure out how many different ways you can put them in there. So I'm just going to put, say, the chlorines on and then see how many different places I can put the chlorines, because everywhere I didn't put a chlorine, I put a fluorine. So you see, you don't have to do all six of them. Just do one of them. And I'm going to, right here, it wouldn't matter because there's the same number, 3 and 3. If I had, say, 4 and 2, then actually I would only do the one that had 2, because all the other positions are going to be occupied by the other element. And so I'm going to pick the one that's smallest and see how many isomers I can make out of that. So let's say I put a chlorine on here. Okay, I put the chlorine there. Now, where can a second chlorine go? Well, it could go here. So that would be okay. Now, where could the third one go? Well, it could go here. Here and here would be the same. Here and here would be the same. Here and here would be the same. So there's 3 different places where I could put 3 chlorines like that. I can put them one like this. Now, what if I did it? These have 1 chlorine on each of the 3 axes, one on X, one on Y, and one on Z. Now let's see is there another way that I could do this? Well, a while ago we put the first one here, so let's put this one here. Well, if I put it in the others in either one of these 2 places, then I'm going to generate this one again. So let's put it on the same one. Okay, so this one had a chlorine on all 3 of the axes. This one's got 2 on one of the axes and 1 somewhere else. I could put it here, or here, or here, or here. They would all be equivalent to this one. You see, if I put this chlorine, say down here, to get this structure, I just flip it over, get that one. What if I put it here? Well, if I put it here, I can put it here just by flipping it over this way. You see, there's only 2 places I can put the 3 chlorines. I can put all 3 of them on separate axes, or I can put 2 on one of the axes and 1 on one of the others. So there's 2 isomers for the 3 chlorines. The fluorines go in the other places. So how many isomers can we get?
Dr. Pearson,
Yes.
how did you know that was a central atom equation and not the other kind that you just did?
Oh, well, let's think about it. If I had sulfur in group 6, what would sulfur have to look like? It would be like this, right? So sulfur by the Tinker Toy model should have 2 lone pairs and 2 bonds, just like oxygen does. But you see, I've got 6 things to attach to something that only has 2 places. It has to be this kind, okay, to get all 6 of those things attached to sulfur. The only way sulfur can be bonded like that, like the Tinker Toy model, stretched out model like we had up here, is that it has to be like this. The other way I can reject that one up there as strung out in any way is because what does chlorine and fluorine both look like? Well, it's grouped in 7. So each one of them could only form 1 bond. So I can't make but 1 bond with the chlorine, so chlorine can't be in the middle. So there's no way you can draw Cl3F3 in a structure that obeys the octet rules. It has to be a central atom.
So the strung out atoms have to obey the octet rules, but the central molecules don't.
That's true.
Okay.
That's right. Yes. And if you can draw the structure using the Tinker-Toy model with the octet rule, you can save yourself some time maybe with the math. But you can do it with the math as long as it does have a central atom. Now, back up here with these others, I could not draw a central atom molecule for H2CCHCN. There's no way I could attach all of those atoms to one atom. So looking at it, I wouldn't even think about trying to do math on that. I would have to do the Tinker-Toy model. Down here you might imagine, but you can reject it pretty quickly, because if you look at the Lewis dot structure for sulfur, it only forms 2 bonds. Chlorine only forms 1 bond, and fluorine only forms 1 bond. So it can't work. It can't work for these. So it has to be. And then I'm looking at it, and there is one unique atom, sulfur, and it appears everything's attached to it. So I'm going to do the math. And if I did the math, I would come out with AX6, and then I would draw the octahedron and do what we did. How many different isomers can I make? And I'm going to do it by looking at the structure I've got and trying to figure out then how many different ways I can put the minimum number of things attached. Like this is 3 chlorines and 3 fluorines. What if it had been, say, 3 chlorines and 2 fluorines on some molecule? Couldn't be S if it's uncharged. But if I had 5 things with 2 and 3, so back over here, this is not this problem, but suppose I had 5 things. And I say, okay, I've got 2 chlorines and 3 fluorines to put on. Well, I'm going to do the 2 chlorines. How many ways can I put 2 chlorines on? I can put one here and one here. Now, that's one here, one axial, one equatorial. That's the same if I put this chlorine over here or this chlorine over there. So that's one of the isomers, one in the axial and one in the equatorial. How many other ways can we do it? Let's see. I could put both of them on the axial position. Now that one's different from that one. And that's 2 on the axial positions. So that's the second isomer. Is there another one? Yes, there is. I can put both of them in the equatorial plane. So I can have axial equatorial, 2 equatorial, or 2 axial. That's the 3 isomers that could be there. And the fluorines, I'm going to put the fluorines in the remaining positions wherever they are. I don't want them to bother me while I'm trying to figure out how many isomers I can get. I got that just by looking at the minimum number. I had 2 chlorines and 3 fluorines, so I tried to find out how many isomers can I make with the 2 chlorines, and I found 3. So these are the 3 isomers that would exist for this molecule. Which one would you actually make? I don't know. My guess would be we might get a little, if I made these products, just took sulfur and fluorine and chlorine and mixed them together until they all reacted and made, I set the stoichiometry so that I would only have 2 chlorines and 3 fluorines. For every 2 chlorines in the mixture, I'd have 3 fluorines. That would be my stoichiometric mix. I would try to figure out, well, which products would I get? These. Now I said I thought this one might favor the others because chlorine is a bigger atom than fluorine. I'm thinking chlorines are further apart in this one than even in this one. So my guess is going to be like that because the chlorines might do something like this. But the chlorines could do what electrons do. It could go the first one in here and the other one try to avoid it. which would lead to this structure. So I'm guessing one of these two is probably going to be the most prominent, depending on how the reaction happens. But that's a story for organic, not for here. Okay. Now, the next one is a real easy problem. So this is intended to raise the average, but it tests the concept. You have to be able to get numbers of valence electrons, and we want to know the valence electrons in SF3 1 minus. Well, we've done it several times already. Sulfur's in group 6, there's 6 of them. There's 3 fluorines. Fluorine's in group 7. I add 1 electron for the charge. 21, 22, this is going to be 28. And that's response D on this question. What is the hybridization of sulfur in that molecule? Okay, well, I've got to go ahead and do my math. We had 28 divided by 8. This is number 9. And that would be 3 and 24. And the remainder is 4. Divided by 2 is 2. It's an AX3 E2 type. So the total of them is 5. And to get hybridization, I'm going to do S, 1, 2, 3 for P, and D, 1, 2, 3, 4, 5, D orbitals. I need to put in 5, 1, 2, 3, 4, 5. I would have S, P3, 1, 2, 3, D. So the hybridization for this molecule is sp3d or dsp3. And if you remember my discussion, I told you that's life or death. And that the one that's listed here is this one, and it's C. What is a molecular shape? Now, this is again a warning. Molecular shape of SF3 1 minus. Okay, I've already got the VSEPR is AX3 E2, and that's a trigonal bipyramid. 2 lone pairs go here, and the sulfur goes here, the fluorine goes here, the fluorine goes here, the fluorine goes here. Of course, the charge of this thing is -1. But that's what it looks like, and it said molecular shape. Electronic shape is trigonal bipyramid, but the molecular shape is what you get without the lone pairs. So it's T-shape. We've seen that before. It's A. Number 11. Now, this one is not the same molecule we had way up there in the beginning. We want sigma and pi bonds in a strung out molecule, HC, CH, CN. Okay? Now, first thing I'm going to do is take care of the hydrogen. It belongs down here. So I'm going to put oxygen. I'm going to put a carbon, another carbon. I'm going to put a hydrogen down here off to the side. Then I'm going to put another carbon. Then I'm going to put a nitrogen. And now I'm going to attach everything. And I'll answer this sigma question right now. 1, 2, 3, 4, 5. It's got 5 sigmas. Don't forget to count that one. 1, 2, 3, 4, 5. Now, next thing I'm going to do is put the lone pair on nitrogen. Remember, nitrogen, to review, oxygen has to have 2 lone pairs and 2 bonds. Carbon has to have 4 bonds. nitrogen has to have 3 bonds and a lone pair. So I'm going to put the lone pair on. Now I'm going to start over here, and I'm going to put in additional bonds to make these things work. Oxygen needs 2 bonds. It's only got 1. So I'm going to put another one there. That makes the oxygen right. And the lone pairs on oxygen, I probably should have put in already. But now I've got 2 bonds and 2 lone pairs on that oxygen. That's good for oxygen. This carbon is not done. It's got 1, 2, 3 bonds. I can't put lone pairs on it. Carbon never has lone pairs as carbon molecules. I have to put another bond. Now that makes carbon work. And this carbon has 4 bonds. It works. The hydrogen has 1. It works. So this carbon is good. This one is not. Again, I can't put the bonds here. I have to put the extra bonds over here. Now that makes that carbon work. That makes that nitrogen work. Now, let's look at the bonds I put in. I put in that one and that one. Those are pi bonds. That one, 1, 2, 3. 1, 2, 3, 4 pi bonds. So I've got 4 pi bonds. So my answer should be 5 sigma, 4 pi, and that's answer A on number 11. And this is a similar question to one of the others we've done, but with a different molecule. And it's the hybridization of the middle carbon. It's in the same molecule. Let me go down here and recopy the structure that we had. We had oxygen, okay. All right, I think I faithfully copied the Lewis structure that we came up with for that molecule. And again, we're looking at the central atom, middle carbon atom, the one in the middle of the other 2. Okay, and it has 1, 2, 3 atoms attached. It's an AX3. And AX3, so it's 3 things attached. So again, if I'm doing hybridization, that's S. 1, 2, 3 is P. I don't really need the D's on this one. S, P, D. I have 3 things. 1, 2, 3. So that's 3 things. 1, 2, 3. So I need sp2. So the sp2 hybridization is answer D. You know, while we're here, let me look ahead and see what the next one is. Okay, yeah, it's bond angle. So let's go ahead and do that. And then I'm going to be, we want bond angle. And it's, in this case, it is the C bond angle that we want to get. Same one. So I'll tell you what I'm going to do. I'm going to glue this down here. And I'm going to put a carbon here, hydrogen here, and going down like this now. And that's this carbon. Now, let's put this carbon here and the nitrogen here. And now we're going to go over to the other side. And this was a double bond to this carbon and another double bond to this oxygen and a lone pair, 2 lone pairs on this oxygen. So this is what that molecule is actually going to look at. Like the bond angle, the C bond angle from AX3 here is trigonoplanar, so it's 120. Now, I drew this in a straight line for a reason. This one would be AX2, right? That's AX, 2 atoms attached to this one. That's linear. That angle is 120 degrees. Now we can't see this one, But because we can't see electrons, but how would they be oriented relative to each other? Well, what is this? This is AXE2. AXE2. So that's three things attached. And this angle would be 120 degrees also, as would this one if we could see it, and this one if we could see it. And then over here, the same thing. AX2 is linear. That's 180 degrees. I said 120 here, sorry. 180 is a linear angle, Earl. And that's 180. And then if I'm doing this one, it's AXE. That would be linear as well. So this angle here would be also 180 degrees. So is that important? Maybe not, but think about it. Suppose this pair of electrons is going to react with something and form a bond right there. Maybe in organic chemistry, you're going to do something to form a bond right there. Where's it going to form? Well, this new piece of the molecule is going to come in right there and be in a straight line with this. And you're going to know, my guess is, nitrogen is very electronegative to carbon, so this is going to be negative, and the negative, a lot of the negative charge is sticking out on this side of that molecule. So if this is negatively charged in this region, it's going to look for nuclei. So positive charge. So this thing would be called a nucleophile. The nucleophilic attack of this on this molecule would occur at the most positive center in this molecule with that pair of electrons on this one. That's where your bond's going to form. So please keep this stuff in mind. It's going to convert organic chemistry into an endless exercise of memorizing stuff into something that makes sense. And it makes sense. And we got all of that. We know exactly the shape of this molecule. We know it's flat as a pancake. We know that the angle between these two big pieces is 120 degrees. And the angle up here, if I'm going to attack this carbon, it's going to come in right there. Whatever's attacking is going to come in right there. So I'll know exactly what kind of shape I'm going to get for the resulting molecule. So really think about that. This is going to really be important later. And you getting it here in freshman chemistry, Gen Chem 1.
Hey, Dr. Pearson.
Yes.
Just quick question. How do you know for sure that this molecule isn't just a carbon atom with 5 things attached?
You cannot have anything but 4 bonds to carbon. Remember? I told you back up way when we were doing Tinker Toys. And please now, if you go to organic chemistry, don't you dare draw a structure with 5 bonds to carbon, because your professor is going to want to know who taught you Gen Chem 1. Don't tell him. Tell him you forgot. No, I'm having some fun with you. But no, you can only have 4 bonds to carbon. Every carbon always, forever and ever will have exactly 4 bonds.
Okay.
That's all.
Dr. Pearson?
Never more than 4, never less than 4. Carbon has 4 bonds only. And it does in all of these structures we drew right here, and it does in every molecule you ever make with
Dr. Pearson?
Yes.
How do we know, like, so you said for carbon, I mean, obviously that's 4 bonds, but earlier we had a nitrogen that had like 6. How do we know?
No. Not nitrogen. If we did, we screwed up big time.
We did. We had
Nitrogen's in
something
group
of that
1.
nature because one of the other students asked about it, and you said when you're using these central atoms, you get to change things up.
Okay, well, I'm not sure what we were talking about, but if I'm doing hydrogen and lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Hydrogen has 1 bond. Lithium and all of its things would have 1 bond. They're in group 1. Beryllium is in group 2. It's going to have 2 bonds attached. They're going to be 120 degrees. Boron is in group 3. It's going to have 3 bonds. no lone pairs. Carbon is in group 4. It's going to have 4 bonds in all of its structures. Nitrogen and all of its structures is going to have 2 bonds, a 1 lone pair and 3 bonds, always, forever. And oxygen is going to have 2 pairs and 2 bonds. And fluorine is going to have 3 pairs and 1 bond. It's going to go 1 bond, 2 bonds, 3 bonds, 4 bonds, 3 bonds, 2 bonds, 1 bond. 3 pairs, 2 pairs, 1 pair, no pair, no pair, no pair, no pair. Okay? That's always the case for row 1. It never can have anything but that. Now, that's because you only have s and p orbitals available. It takes 2 to fill an s and 6 to fill a p. That gives you 8, an octet. These can never have more than 8 electrons around them under any circumstances. You cannot make a nitrogen. You cannot make a nitrogen have 5 bonds. Now, phosphorus you can. Phosphorus is in the next row down, and that's the 3rd row. There's 3s and 3p available in phosphorus, but it has an empty 3d. The 3d can be involved in bonding. So you can have up to 5 pairs around phosphorus. You can have up to 5 bonds around phosphorus. When you go, so oxygen can't, but sulfur can. Sulfur's in the next row. So sulfur can have up to 6 pairs around it. If you go down to iodine in group 7, it can have up to 7 pairs of electrons. It can have up to 14 electrons around it. Now, we haven't dealt with anything with 7 pairs, but it can. This molecule, if you mix iodine with fluorine, one of the products you can make is IF7. You can actually make that. And it's certainly not an octet rule molecule, and it's more than anything we've got when we did structure so far. But it would have to be sp3d3 to get 7 things around it. We don't know what that looks like. We never talked about that kind of hybridization, and we won't in Gen Chem 1. I mean, if you go to inorganic chemistry as a junior or senior, they might talk about those kinds of bonds, but nothing more than 6 pairs, and none of the first row elements can have anything except an octet or less. Beryllium is only going to have 4. It's got 2 bonds, and that's just 4 electrons.
So the most amount of bonds you can have is 7 because your valence electrons will run out after that
Well, not
on a central atom.
totally. I told you that's all we're going to look at. But it is true that a lot of the elements do, if you're in the 4th row, for example, you can have 4s, 4p, 4d, and 4f. You can even involve the f orbitals in row 4. So you can generate hybridizations involving f orbitals that we never even thought about here.
So you can have more bonds than valence electrons in certain cases?
That's right, yes.
Okay.
You can. But they're going to be these math models, things that we've been doing. Okay, all right, so let's go right on. Number 14. Which of the following would associate into ions in water and will be a strong electrolyte? And we're looking for strong electrolytes. Generally, when you're talking about electrolytes, you have to have ions to make something carry an electric current. When we're talking about strong electrolytes, we're talking about things that dissociate completely in water to create ions. Well, if I had HX, and I want that to be a strong acid, these will be strong acids. And if you put, say, HCl, if you put HCl into water, you get completely H plus aqueous and Cl minus aqueous. So HCl is going to be an electrolyte because it produces a lot of ions. It's going to be a strong electrolyte because for every 1 mole of this, you'll get 1 mole of this ion and 1 mole of this ion. So you're going to create a lot of ions. The strong acids are HCl, HBr, HI, H2SO4, HNO3, and HClO4. These I've memorized, 1, 2, 3, 4, 5, 6 of them. So if it's one of these, it's a strong electrolyte because it's a strong acid. The other way you can get strong electrolytes is if you had strong bases. And they're things like NaOH and, well, all the group 1 hydroxides, lithium, sodium, potassium, rubidium, cesium, forget about francium. All of those hydroxides would be strong electrolytes. And we're going to count also group 2, like magnesium and calcium and strontium. I guess barium comes first, barium, strontium, and others. So these hydroxides are strong, although actually not all of them are. But we're going to count them. Group 1 and group 2 hydroxides are strong bases. Now, do we need to memorize that? We're going to talk now about solubility rules. Now, you do have to memorize these. And the solubility rules, there's, I think, 5 or 6 on the list that I gave you, and they're in numerical order of importance. The ones that are at the top of the list are more important than the ones down below if you get a crisscross or conflict. The first rule, I think, is all chlorides, bromides, iodides, acetates, nitrates are soluble, except the chlorides, bromides, and iodides of silver, mercury, and lead are insoluble. So if you learn those solubility rules, that will tell you which things will break up. And one of the rules is for hydroxides. All hydroxides are insoluble except group 1 and some of group 2 hydroxides. So if you do the solubility rules, you know the only hydroxides that are soluble, strong electrolytes, are group 1 and group 2 hydroxides. So these two complement each other. And so you wouldn't have to memorize that if you memorize the solubility rules. And the solubility rules will deal with all the other things. Now, here are the compounds that we're talking about. A is silver chloride. Is that a strong electrolyte? By the solubility rules, we're looking at this chloride. All chlorides are soluble except silver, mercury 1, and lead plus 2. So this is a weak electrolyte. It's insoluble, meaning the silver ion and the chloride stay stuck together in a solid at the bottom, a precipitate, and they don't separate into ions. So this one certainly is not the correct answer. B, HClO4. Well, this one is a strong acids. This one is a strong electrolyte. Now, I don't see an answer that says both B and D or whatever. So I can stop right there. That's the only answer that works. Let's eliminate the others though. C is H2S. I said that because you should play the test. When you know what the answer is, don't pursue it further. I mean, you can double check to see that it's correct. The others, eliminate the others, but I might do that as a second pass on the test if I have time still left over. H2S It's not HCl, HBr, HI, H2SO4, HNO3, HClO4. It's weak. So it's not that one. And D is FeOH3. Well, it is a hydroxide. Is it a soluble hydroxide? Well, solubility rule says the hydroxides are all insoluble except group 1 and group 2. Well, that's not a group 1 or group 2. So it's insoluble. It's going to stay as a solid, not break up. It would be weak. So the only answer that's correct is this one. So this is an exercise in using the solubility rules and whether you memorize the 6 strong acids or not. And number 15 is going to be based on the same idea, which using the activity series on the front of the exam, reactions A, B, C, or D will take place in aqueous solution. For this practice exam, use the activity series in the lecture on the PowerPoint slides. Don't have the activity series available to me, but I'll tell you what you would find. If I want to make A happen, then it's a single replacement reaction. Silver is going to push copper out. Okay? Now, if that did take place, silver would need to be more active than copper. On the activity series, copper, all of those down there are less than hydrogen, but copper is above silver. So no, that reaction will not happen going this direction. If it were going the other way, it would. Copper can displace silver because copper is more reactive than silver. So this reaction doesn't happen, but its reverse reaction does. Now that's going to always be true for single replacement reactions. If the forward reaction doesn't happen, the reverse reaction does. If the forward reaction does, the reverse reaction doesn't. Okay, now, will silver be able to displace hydrogen? No. Hydrogen is above both copper and silver and the activity series. So this reaction would not happen. But yes, if you took silver chloride and you bubbled hydrogen through it, you would displace the silver and make hydrochloric acid. That reaction would happen. The other one wouldn't. Again, copper and hydrochloric acid. No, copper is below hydrogen, so copper can't push hydrogen out. Hydrogen is more reactive than copper. And again, hydrogen can push copper out. The reverse reaction can happen. Well, the last reaction has to be the correct one. And I'm sorry, I forgot to show you my screen. I should have been showing it to you for that one. Here's what we're looking at. And what I'm saying is that silver on the activity series, maybe hydrogen is here and copper is here and silver is here in that order. So silver is below copper, it won't react. Silver is below hydrogen, it won't react. Copper is below hydrogen, it won't react. But iron, hydrogen is here and iron is up there somewhere. Iron can push hydrogen out. So hydrogen will react with hydrochloric acid to make iron 3 chloride and hydrogen gas. That one will occur. The reverse one would not. So if you have the activity series in front of you, and you would on the exam, it would either be an attached page or it would be a portion of the activity series would be given over here in the white space so that you'd have it right there by the reaction. If I gave you probably a white space activity series, it would be a very short, abbreviated one. I've got 1, 2, 3, 4, 5, 6, 7 lines is the maximum I could use to create an activity series. So I couldn't give you the whole table, but I could give you what you need for that particular problem. That's probably the way I would do it, especially on D2L. I kind of have to do that. Now, this says, assuming this reaction does take place, HNO2, Al2, S3, making AlNO2, taken 3 times, and 3 H2S. Suppose that does take place. And I want to know which of these reactions down below represent the net ionic equation. Now, what we have to do to get the ionic equation, this is the molecular equation. So we're going to write this the way it would appear if you put it all in aqueous solution. Now, HNO2, would we separate HNO2 or keep it together like in this one? Well, we separate acids when it's hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, perchloric, iodic. Yeah, okay. This is not one of those 6. It does not separate. So at this stage, I know A is a possibility and B is a possibility, and I can eliminate B and D. Well, maybe I can't eliminate D yet because I don't know whether all of this rest of this stuff works. Now, what about Al2S3? Would it separate? Well, what are the solubility rules on sulfides? All sulfides are insoluble except group 1 and ammonium. So Al2S3 is not one of those group 1 or ammonium sulfides. So it stays as a solid. So that's good. That's still good. So these 2 are still going. Either one of these 2. And this one maybe is a possibility because one of these might be eliminated over here. Now, aluminum nitrite, would we separate it? Well, solubility rules. All nitrates, acetates, and perchlorates are soluble. That is a nitrite. It is soluble. It does separate. It separates into 2 aluminum plus 3. Aluminum is plus 3 in this compound. Nitrite's minus 1. So it's 2 aluminum with a plus 3 charge, and 2 times 3 is 6 nitrites with a minus 1 charge. So this one is correct, and so is this one so far. So both of these are good. If those both went wrong, then this one would work. What about H2S? Does it separate or not? That's going to distinguish these 2. It's an acid, H2S. Is it HCl, HBr, HI, HNO3, H2SO4, or HClO4? No, it's not. It does not separate. This is correct. This is not. Now, this is not correct. Okay? So if you got your solubility rules and the 6 acids down, that will be an easy problem. So there's 2 questions now that we've come up with that you're going to have to know the 6 strong acids and the solubility rules in order to get the answer. I think I've done this one in lecture already, but just to remind you how we would go about doing this problem. We're getting the oxidation numbers for, this is number 17, and the compound is ZnUO2 parenthesis C2 H3O2, and there's 4 of them. And now I've got to get the charge numbers of everything. So I'm going to start left to right and divide off the things that I know. Zinc is always +2 in all of its compounds. So this is going to be a +2. So I know that all the things over here has to be -2 total. Now I'm going to divide off this part into what I know. I know what that is. That's acetate, that's -1. There's 4 of them, that's -4. So if I want the rest of this to become -2, what does this have to be? That's right, it has to be +2. So +2 with -4 gives me -2. -2 with a +2 gives me 0 for the compound, and it doesn't have a charge up here given. there's no charge. So I know UO2 has to be a +2. So I'm going to go over here. UO2 has to be a +2. Now let's separate these. On this side, I've got 2 times -2 is -4. So what does uranium have to be in order that the total is +2? Well, it has to be a +6. +2 - 4, +6 - 4 is +2. So uranium is +6 in this compound. That's answer A. Okay, now, okay, and here we go. Number 18. We've got phosphorus, the compound, the reaction, I'll copy it over here for you instead of going over to the screen. It's P4 and 20 HNO2s and 8 waters. And it's going to go to 12 H2PO4s and 20 NOs. Okay, and what we're asking for is oxidized and reduced. Which of these species is oxidized and which one is reduced? Now, what I'm going to do is I'm going to remind myself oxidation is an increase in the charge on the atom. Reduction is the reverse of that, the decrease. Okay, so I need to know the charge numbers in all of these atoms to pick out what's oxidized and reduced. So there's a phosphorus right there, and it's an element. So the oxidation number of phosphorus in an element, or any element by itself, is 0. What is it in this compound over here? Well, hydrogen is going to be +2 for 2 of them, and oxygen is going to be -8 for 4 of them. So then phosphorus needs to be +6.
Hey, Dr. Pearson.
Yes.
Real quick, on my test, I don't know if it was different for yours, but it's HNO3, and then that's H3PO4, not H2.
Oh, hey, where did I get that? It's H3. Of course it is. H3PO4. I copied it wrong. Like I told you a while ago, my glasses. My glasses are getting bad, and my bifocal is right down on the very tip edge of my glasses. So sometimes if I don't push my glasses up, then I can't distinguish those subscripts like I should. So that should have been H3PO4. And I was really seriously bothered by that because I knew phosphorus ought to be +5 in this compound instead of +6. Now it is. So it's +5. So phosphorus goes from 0 to 5. So I can go down here and say oxidation, phosphorus is oxidized. Thank you for pointing that out to me. It caused some mistakes. Okay, now, the other elements, I'm expecting oxygen to stay what it is, and hydrogen to stay what it is, but nitrogen, I can clearly see it's in a different form here than here. And if this one's oxidized, this one better be reduced. Let's see if it is. So in this compound, oxygen is -2, and 2 of them would give me -4. And hydrogen is a +1. So nitrogen would need to be a +3 in that compound. Now, if I go over here, oxygen is -2, so nitrogen is +2 in this compound. Sure enough, the nitrogen or the compound it's in, HNO2, is reduced. So that should be the answer to this question. And it's response B. It says P4 is oxidized and HNO2 is reduced. So that is the correct answer. And it's B on your exam.
Dr. Pearson,
Yes.
one more question, I'm sorry. Where do you
No.
get the 5 from in the H3PO4 for
Oh, okay. I'll put it down here. It's all cramped up there. H3PO4. I'm assigning these things what they have to figure out what that one is. Oxygen's always -2, so 4 times -2 would be -8 from the 4 oxygens. Hydrogen is +1, and 3 of them would be +3. So now I'm trying to figure out what do I need to add to this so I have +8 and -8. That'd be a +5. So if phosphorus is +5, hydrogen, the 3 hydrogens +3, I've got +8 here, and I've got -8 over here, and the charge on the compound is 0, so that'll be correct. So that's how I got the +5. I assigned oxygen and hydrogen first, because I know what they are. The phosphorus is the one that was variable. Okay, are we good? All right, let's moving right along. Okay, we're getting molecular formula. Number 19 is the molecular formula for a compound that is 62.78% mercury. It is 17.19% manganese, and it's 20.03% oxygen. Okay, so there is the percentage composition. We got another piece of information. Molecular weight, molar mass of the compound is 639.06. Oh, gee. I didn't tell you this. Be real quiet now. The correct answer is the only one probably with a molecular weight of 639.06. It'll be quicker to calculate the molecular weight of the compounds than it is the way I'm going to show you. Okay? Don't tell anybody. Okay. All right. Sometimes the ham in me comes out. Okay, so I've got a formula. The compound is Hg. It's got Mn, and it's got O in it. So I'm going to call that X and Y and Z. That's going to be the formula of the compound. HgXMNYOZ is the formula for the compound. So the way we showed you, we took the percent. I'm going to do Hg, and I'm going to ratio that to the second one I've got is the percent of Mn. And in the problem, this number is 62.78. This number is 17.19. And now, that has to be, I'm looking at the mercury stuff. How much mercury is in my compound? X of them. I've got X. And the molecular weight of mercury is 200 point something or other. 0.7 maybe? I don't remember. I've used them so many times that I've got a lot of them memorized. Mercury is not one of them. 200.59. I said 0.7 is 0.6. 200.59. Now, how much manganese do we have? Well, the manganese in the formula is Y, and the molecular weight of manganese, I remember chromium, don't remember manganese. 54.938. 54.938. Okay, now I've got my setup. I'll cross multiply. That gives me 62.78 times Y times 54.938 equals 17.19 times X times 200.59. All right, now let's do our math. 62.78 times 54.938 is 3449.00764, and it's Y equals this times X is 17.19 times 200.59 is 3448.121421. Almost transpose those digits. Okay, so 3449, 3448, essentially 1y equals 1x. So x is 1 and y is 1. Okay, let's hold that thought. So my formula is Hg1Mn1OZ. So that's my formula. Now let's ratio mercury to oxygen, the only one we don't know. We've got percent of mercury over percent of oxygen. Percent of mercury was 62.78. The percent of oxygen is 20.03. Now, the number of mercuries is 1, and the atomic weight of mercury was 200.59. And now, the oxygens, there are Z of them, and the atomic weight is 16. 15.9994. I'm just going to call it 16. Cross multiply Z times 62.78 times 16 equals 20.03 times 1 times 200.59. Now to get Z, I need to make this times this and divide by each one of these. So Z is going to be equal to, so I take this side, my calculator instead of my phone, 20.03 times 200.59 20.03 times 200 divided by 62.78 and divided by 16. That comes out to be 3.99980 0.98156. So Z is equal to 4. So my formula is HgMnO4. Okay? Well, let's see. Wow, that's one of the answers, but guess what's the wrong one? What's wrong? This is the empirical formula. The molecular formula is some multiple of this. So I could multiply this through by 2. I could have Hg2Mn2O8. That would be a possible. I could have Hg3Mn3O12. That would be a possibility. And so which is it? The way you tell is you do the empirical weight here, mercury, as we're adding up the molecular weight, I'll say, for the compound that we just calculated. Mercury is 200.59. Manganese is manganese is, where did I do it? Up here. It's 54.938. 54.938 plus 4 times 16. So 200.59, 54.938, 4 times 16 is 319.528. Now, the problem formula, molecular weight, that was given is 639.06. So if I take this number, 639.06, divide by this one.
Can you move your page up?
Oh, sorry about that.
Thank you.
Yeah, there you go. This thing's got in the way. Get it out of the way. We don't need it anymore. Okay, so I'm going to take 639 and divide by 319. So 639.06 divided by the answer I still have is 2. It comes out to be 2.0000. So this is the formula. It's Hg2Mn2O8. Well, I don't see that, but I do see Hg2Mn O4 2, which is the same thing. So this is the correct formula. And looking at this, I could even tell you what the compound is, what the name of it is. It's this Hg2, permanganate is -1. So this is -2. Hg2 plus 2 is mercury 1. And this is permanganate. So this is mercury 1 permanganate. Now, we got the problem. Everything works great. Now, I'll tell you as a chemist, there's no way in the world you can make that compound, mercury 1 permanganate. Permanganate is an extremely powerful oxidizing agent, and mercury 1 could be oxidized to mercury 2. There is no way this compound actually exists. And the problem says this compound may not actually exist. I'm betting on it. It won't. Okay, but remember what I whispered to you? You would have got that molecular weight for that compound a lot quicker than you would have done it this way. So if you are ever put into that position on my exams or on a standardized exam or somebody else's exam, they think they're making it tough by giving you the molecular weight and forcing you to get the empirical formula and doing all that. Maybe they don't know. All you got to do is get the molecular weight. That is, if it's a multiple choice question. If it's not a multiple choice question, then you're forced to do it, I guess. All right, number 20. Let's see. 29 pages there. Let's go to another one. Pen is getting a little weak too. Okay. Molar mass for a compound. Again, this one's going to be a gift problem. At this stage, the compound is UO2, 3, PO4, 2. That's uranyl phosphate is the name of the compound, but we just want the molecular weight. We got 3 uraniums in here, no other uranium. I've got 2 phosphoruses. I'm going to take care of that one next because phosphorus is only here. But oxygen, I've got 2 times 3 is 6 here, and 2 times 4 is 8 here. So I've got a total of 14 oxygens. So now it's just a matter of 238. And I looked that up somewhere. 238.03, I'm pretty sure. But we would make sure. Yeah, 238.03. That's uranium. Phosphorus is 30.97, I think. You know, it's probably time for me to retire. You've got this many molecular weights in your head, atomic weights in your head, it's too full. 230.97. Next digit is a 4. So that's right. And you've got oxygen memorized already, I'm sure. And there's, so I need to take 3 times that, and 2 times that, and 14 times that, and we got it. So it's 3 times 2, 238.03, plus 2 times 30.97, plus 14 times 16. 2 times 238 plus 2 times 30.97 plus 14 times 16. Yes, that should be it. Oh, look at that number. 1000.03. That's kind of unusual, isn't it, for molecular weight? Okay. I used some extra digits here that I didn't on there. The answer on the problem is 999.93. So that's the answer we got. That's what's shown on the test. So that's the correct answer. It's D. The others are not even close. 731, 465, or 93. That's the only one that's in that range. So that's okay. And I'm pretty sure I probably made that 31 and maybe 238 up here is what I did. I didn't use all of the significant figures or I would have gotten that nice number. Okay, how many grams of nitrogen are there in 23.5 grams of this compound? Please pay attention. Some of you are going to look at this and say, oh, I got to get the percentage of oxygen or the percentage of nitrogen in this compound. I got to do blah, blah, blah. No, you don't. Here's what's given in the problem. 23.5 grams. I'm going to just abbreviate. Well, no, I've got to put it up here. It's NH4. I forget you're not watching what I'm watching. 2 NH4 2 C2O4. And it says molecular weight is 124.1. Now that's all the data. What if I asked you for the name of that? Would you have gotten this? Ammonium oxalate. Or would you have gone for response B that said diammonium phosphate, oxalate? You don't need the di because it's oxalate, and that's C2O4 minus 2. You don't need the di because this is ammonium, NH4, and it's plus 1. There has to be 2 of them. You don't need diammonium oxalate. It's just ammonium oxalate. That's the name of that compound. If you Google it, it's going to tell you it's diammonium oxalate. It is not. It's not. That little, high school genius that wrote that website wasn't as smart as he thought he was. Okay. All right. So here is the correct formula, correct name. Now, here's what we're going to do to work the problem. A given amount with a given unit, okay? It's 3.5 grams of this compound. Now, right down here, I'm just going to abbreviate it CMPD, but CMPD is ammonium oxalate. Now I'm going to put my conversion factor in. I want this unit to go down here, grams of the compound. Now, what does the problem ask for? It says how many grams of nitrogen. So I want grams of nitrogen in here. Now I want to put numbers in here that make the numerator and denominator represent the same amount of stuff. If I had 124.1 grams of compound, I would have a mole of the compound. How many moles of nitrogen would that be? 2. So the grams of nitrogen would be 2 times 14. So 2 times 14 grams of the compound, grams of nitrogen, is the same sample that weighs 124.1 grams. Numerator and denominator are equivalent. They're set up in a way that this unit cancels. The unit that I got for the answer is the unit asked for in the problem. That number is correct. You do that in one step with one set of calculations on your calculator. I'm going to do 23.5. I'm going to multiply it by 2 and multiply it by 14 and divide it by 124.1. And I get 5.31. In the problem, that's response B is the correct answer. Now, like I said, I did not convert grams of this to moles of this. I did not convert from moles of compound to moles of nitrogen. And I did not convert from grams of nitrogen, moles of nitrogen to grams of nitrogen. I didn't do that the hard way. I did it as any unit conversion. If I told you convert 23.5 inches into centimeters, you'd work it this way. So this stuff works the same way. I mean, just because we're using chemical stuff doesn't make it any different or any harder or any easier than doing the conversions of masses or volumes. It could be 23.4 liters. How many cubic inches would that be? Well, that's a harder problem than this one, but it works the same way. Given number, given unit, ask unit. Number that belongs with this unit, number that belongs with this unit in that compound. Poof. See how quick that is? That's 30 seconds on the test, done this way. It's 2 or 3 minutes done. I mean, if you're going to first convert and get the percentage of nitrogen in that compound and then take that and calculate the mass of the nitrogen from the percentage that it is and the mass of the sample, blah, 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 blah. I ain't doing it, as we say in Kentucky. Okay. This is stoichiometry problems now. So let's see if we still remember what we were doing. The problem that we're looking at is this one, 8C3, CH3, NH2. In organic, they'll call that methylamine. And 13 HClO4, that's perchloric acid. It makes 8 NO2s, nitrogen dioxide, plus 8 carbon dioxide, plus 20 H2O, plus 13 HCl. Hey man, that would be a good equation to balance, wouldn't it? Wow, That'd be fun. Okay, what mass of nitrogen dioxide can form from 3.5 moles of perchloric acid? I'm going to recopy the things just in this problem. There's 13 HClO4s, and it wants to know the nitrogen dioxide, and there's 8 NO2s. These are the only two things in this problem, so I'm going to ignore the rest of the stuff for this problem. We have 3.5 moles of this. My unit is moles. How many moles does the equation show? 13 moles. And it wants to know what mass. So I'm going to say how many grams. And what's the equation show in grams? Well, it's 8 times the molar mass of NO2. It's given in the problem, it's 46.01. Okay, now I'm going to do the quick and dirty setup. I'm going to take 3.5 divided by 13, that's my rebalancing factor, times what's under my question mark, 8 times 46.01. Now you see, there's the rebalancing factor times what's under the question mark, but set up in a way that I can do it on my calculator just with a few keystrokes. So I take this, I'll clear my calculator screen. Okay, 3.5 divided by 13 times 8 times 46.01. The answer is 99. This is 99.098 and a whole bunch of other digits, and it would round off to 3 significant figures, which is what I had in my problem, to 99.1. And that's response C on this test. Okay. Now you see why I told you earlier, when I work problems, I might set this up, and if I'm doing this for one, if you're doing this for one of your other teachers, at least do this step on paper so they can see it. They will recognize that this is the same thing you would have if you put this over here, because this would be mass to moles, 18 over 13, times and then moles to grams would get times this number. They would recognize that. They might wonder, why did you put that there instead of there? But they'll at least recognize you set it up correctly and give you credit for it. If you happen to miss the keystrokes in the answer, you probably get some credit for that setup if it's a partial credit type problem. 23. Okay, same equation, but this was saying what mass of water would form by the reaction of 3.5 grams of this. So I want to know how many grams of water from 3.5 grams of the methylamine, CH3, NH2, and 15 grams of perchloric acid, HClO4. Okay, so now we are using the methylamine. We're using the methylamine, and we're using the perchloric acid, and we're using the water. So let's put those down. We've got 8 CH3 NH2, reacting that with 13 HClO4s, and we're going to 20 waters. Okay, it said how many grams of water. So I want that in grams. and I want to put the equation in grams. So that's 20 moles. The molecular weight of water is 18.02. That's given in the problem. We didn't have to calculate it. And we are reacting 3.5 grams of the methylamine. The equation is showing 8 moles. Molar mass of the methylamine is 31.06. And now this is 13 of this. We're reacting 15 grams of this. The equation is showing 13 moles. The molar mass for perchloric acid is 100.5. So I see from my setup, I've got 2 rebalancing factors, one here and one here, and I have to figure that out before I can do the rest of the problem. So let's do it. 3.5. Well, are you okay with me just dividing this out? It's rebalancing factor 3.5 divided by 8 divided by 31. I'll just write the RBF under this one. So it's 3.5 divided by 8 divided by 31.06. Double check my numbers. 3.5 divided by 8 divided by 31.06. That's correct. So my rebalancing factor here is 0.014008, and some other digits. Let's see if I need them. And then 15 divided by 13 and divided by 100.5. 15 divided by 13 divided by 100.5. This is 0.01148 and a whole bunch of other digits. 114, 014011, this is the limiting reagent. Oh, that's good for me, because once I know that limiting reagent, I'm just going to take that number times 20 times 12. So this one times 20 times 18.02, I'm sorry, is going to be my answer. And it's still on my screen, so I just got to say times 20 times 18.02 is 4.1377, 4.137772675. Now, I want you to know something. I've had students who would have done this for the rebalancing factor. They would have gotten this on their calculator and they'd say 0.01. You know, if you're going to put one significant figure, just guess. You know, never use one significant figure on anything. I mean, we're never going to have a problem where we're just good to one significant figure, probably in any kind of situation in chemistry. So don't round off anything except the final answer. Keep all those digits. Don't copy that down, 0.0114. 500 or whatever it was. Don't copy that down and then recopy it and multiply it out. Waste time, and you would probably round off here. You don't want to do that. The reason why you don't want to do that is when I get this, I'm going to round it off. I needed 3 significant figures. So I'm going to round off to 4.14. Now, that must be exactly one of my answers, or the answers have to be 4.113 to 4.15. If it's in this range, that's correct. If you get a number close to this, but outside of that range, plus or minus 1 here, you got the wrong answer. Go back and check it. Don't look at one of my, suppose you got, one of the other answers is 1.75. Suppose you got an answer that was you made a mistake. You got an answer that's 1.72. That's wrong. It has to agree to that 1.75 answer, if it's right, to plus or minus 1 in that digit. By not rounding off anything and rounding off only the final answer, it tells you whether you got an answer that is correct or just got one that's incorrect and close to something else. Get my answer. Don't get one close to my answer. It's got to be my answer. And if you don't do that, I could have made a mistake. You know, if we were in class together, I'd tell you to raise your hand and I'd come answer your question and double check it. But since I can't do that, I can answer email. Okay, all right. But I'd rather you weren't using email during exams. That's not permitted. Okay, all right. The next one is a nomenclature problem. So maybe I'll show it to you. And we can answer right on screen. Okay, now, which combination of names is correct? And I hope I don't get to that problem I had on the first exam on the nomenclature. I told you that I deliberately wrote oxalate as oxalite to be a wrong answer. It was testing either spelling or the difference between ATE and ITE and all of that stuff. And the speller checker on D2L, it runs while you're making up exams. And since I'm copying and pasting, I take my exam that I've made up on my computer and have security, and then I upload it and paste it into the question on D2L. Well, I pasted it in correctly, the way I wanted it, but it was incorrect. And the speller checker changed it from oxalate to oxalate, which made the answer have two right answers. So I'll double check that on this one to make sure that doesn't happen anymore. But this is the, okay, so the first one is this the way you would name this compound? I'm not going to look at this answer over here. I'm going to look at that and say it's aluminum something. Okay, this is carbonate. Aluminum doesn't need a Roman numeral. That's aluminum carbonate. It's not aluminum carbon trioxide. That one is not a correct answer. Since the question said which one is incorrect, you know what? I'm going to answer A right now and go on. That shows that the others are correct though. 10 in combination with oxygen. Oxygen is -2. That means 10 is +2. So the correct name is 10,2-oxide. That is correct. The third one is a hydroxide, and hydroxide is -1. There's 3 of them, so the iron is +3. So this is iron 3 hydroxide. That's correct. Lithium aluminum hydride. That's a possible name for that compound. In fact, when you get to organic chemistry, you use this compound a lot. It's a very common compound. White crystalline, very stable compound. Lithium aluminum hydride. Okay. The next one is a nomenclature problem as well. What is the name of this compound? Well, PO3 is phosphite. So phosphite is -3. There's 2 of them. It's -6. There's 3 nitrogens that have to be nickels that have to be +6. So each one is +2. So nickel 2 phosphite is the correct answer for this. It's B. Trinickel diphosphite. I'll bet you money if you Google it, you'll find that compound. It's not right. And nickel 3 phosphite is not right. And nickel 2 phosphate is not right. The name of this compound is HClO2. Now, remember, HClO4 is perchlorate. HClO3 is chlorate. HClO2 is chlorite. So this is a chlorite. ITE goes to OUS in naming the acid. So it's chlorous acid. It's not oxygen hydrochloric acid. Actually, that came in as an answer on a test one time. And I thought, hey, That's cute. That looks good. I like it. Wrong, but I like it. Okay, what is the charge of the chromate ion? Chromate is -2. It's CrO4 2 minus. So that's another pretty much gimme type problem. Oh, well, I'm way back up there at the top. How did I get up there? Oh, that's all I got. I want to give you 27 on the practice exam. There's actually 30 on the other exam, and it would be something that somewhere along the line I thought was a really easy question that you ought to be able to get, illustrating some concept or some earth-shattering words of wisdom that I gave you during a lecture sometime or other that I thought everybody will remember that. Okay, so there'll be 3 questions that fall into that category. Okay, now that's where we are. I'm going to pause the record, or